Hi everybody, thank you for having me. So today I'll talk about how to link and stack using orbital invariants. So first I want to just basically, very quickly review the basic idea of heliolink. So if you consider that we have a catalog of detections where each one has n measured parameters, that's usually 2 or 4 because we get RA index or RA deck in rates. Orbits are specified by 6 parameters. Then for each detection in the catalog, you only need 6 minus n more parameters asserted at some common epoch. And then you can calculate the orbit that makes your assertion true for each detection. So you could assert 4 parameters and apply them to all of the detections in your catalog. And if you choose the correct set of 4 parameters, your detections will cluster in some orbital parameter space. And there's a lot of ways to do that. And you can exhaustively scan through that parameter space in order to find all possible linkages. So this GIF is playing. You can see that the orbital parameters are changing with time, and the dots that correspond to the detections are getting closer and closer to truth. That's error caught over about 2 months. So I'll start with the trackle linking problem, because it is a lot less interesting than the single detection problem. So here we have RA DAC and rates, like you have for traditional orbit linking. So I'll start by introducing a state vector formalism to make our math a little easier. So the position of these things is given by the observer's position, plus the topocentric distance times this rho vector, which is given by the RA index of the observation. The velocity is given by the observer's velocity, is basically just the derivative of the position, where rho dot is your is your line of sight velocity. So everything here is measured or known, except for rho and rho dot. So if you can somehow get rho and rho dot, you can have your orbit be fully specified. So one way that we've come up with to do that is to just express rho and rho dot in terms of orbital invariance and the measured parameters. So 2 pretty good orbital parameters, or 2 good invariants are h and e, angular momentum and energy. So if we take those state vectors, plug them into these 2 equations at the top, and do a lot of algebra, you can get down to these 2 equations at the bottom. So hz, where hz is the z component of the angular momentum, which is also a constant of the orbital motion, and it really simplifies your life because you get rid of the vector. And then epsilon here. So this is an equation of two equations of 2 unknowns, the system, and I'll just give you the answer. It turns out that you can crank through that algebra and get a 10th order polynomial in rho. And once you have solved for rho, you solve the orbit. So there's a lot of ways to find the roots of polynomials. There's usually 2 or 4 roots of the polynomial. So there are 2 or 4 valid solutions to your orbit. And then you can just cluster your orbits in the usual way like Matt talked about. So that works. That's done. So there's a lot of ways that you can choose your parameters that you want to assert. You can use R and VR, but that's not ideally because it doesn't admit an analytic solution, like the equation we just talked about. But it is properly specified, so you're only using 2 assertions. You could use 3 values to get an analytic solution, but those aren't properly specified. You're doing more work than you need to. You can use the ATG basis that Gary presented in 2000 for the orbit fitting. And that does admit an analytic solution, and it is properly specified, but it requires that you use the tangent plane, which could be a drawback if you're doing a full sky survey. But this admits an analytic solution and is properly specified. So that's how you do the linking problem for tracklets. So now the detection linking problem, where we just have RA, DAC, and a time. So I'm going to teach you a new orbital basis quickly. So phi is the longitude, and theta is the latitude on the barycentric sphere. So now we can create this right-handed coordinate system, r hat, a hat, d hat, where r hat is into the board, d hat runs up, along lines of declination, and A hat runs left along lines of RA. R is the distance of the body to the coordinate origin. dr is the radial velocity, the velocity along R. V omega is the tangential velocity. And psi is the direction of v omega with respect to A hat. So these orbits over here will be prograde, these will be retrograde, and the state vector that you can write down looks like this. And it's really nice because this is an orthogonal basis, and there's a lot of natural things that you can do with it. So some really nice properties. Here, your angular momentum is just the multiplication of two parameters. The z component of your angular momentum is the multiplication of four of the parameters. Four. And so this is like eta, it's like the rate of motion on the sky. So from the very center is a division of parameters. Yeah, so there's a lot of nice things. But the nicest is that there's a one-to-one mapping between r, vr, v omega, and the semi-major axis, eccentricity, and true anomaly. Okay? And that is independent of your position on the sphere. That's very important. So we have this valid over parameterization, phi theta, a, e, f, psi. But we can do better, right? A and E are constant, and F is always known, since we know A and B. So those are basically like constants of the motion. Psi is not constant, but inclination is constant. So inclination is related to psi by multiplying cosine equals cos theta, cos psi. So if we want a more constant basis, you can use phi theta, A, E, F, and inclination. That's almost a valid orbit parameterization, but you can't actually tell whether the orbit was ascending or descending at the time that you specified the elements. So you need to introduce another element kappa, which is just binary, it's plus or minus 1. So we have this orbit parameterization that we're going to use for linking. And it's really nice, right? So A, E, and I are all constant. F is always known, since we know A and B. So then it follows that we always know your heliocentric distance, R. So here's the geometry of the problem that we have. Here's the sun, the observer, and the observed object. So we have to satisfy this equation with rho, where you're just basically doing a one-dimensional optimization, minimization, root finding problem, and then your orbit is fully specified. So we use this to do linking in dark energy survey data. We grabbed a supernova field, 1 month of data, about 90 images. There were 2.5 million sources brighter than 3 sigma after using a convolutional neural net to remove junk. I set up an ad hoc grid, about 7,000 different orbits to check, and searched for clusters of 6 or more detections over 7 or more days. And then I fit the orbits on the fly to remove false positive linkages. So this is the transient catalog, and big thanks to Ed for preparing the images and masking all the supernovae and stuff that were in these. It was a lot of work. So here's our linking efficiency. So these are tracketless linking, very sparse, and we max out at about 90%, and our mag 50 is at about 24.2, 24.3. There were 4 known TNOs in this field, and we even discovered a new one. So it has these elements. So in the above threshold frames, there were only 6 of them, so it was the fewest that we could have possibly detected, and no 2 images came from the same type. So it was an extremely sparse orbit. So these are the stacks of the above threshold frames, mean and median. On the right, just like Pedro talked about the subthreshold significance about an hour ago. And so, there's significance in both the above threshold and subthreshold frames. This is a Ripley with a 30-day arc right now, because I have not gone back into the data to extend it. Anyway, so that's extremely encouraging. So now I'm going to talk about how linking and stacking are the same thing. Why does it loop on this computer? Well, I'm going to talk about a new project that I've been working on called HelioStack. So our goal here for this demonstration is to stack searching for subthreshold Neptune trojans in a 7-day subset of the data that I just talked about. The algorithm does work on the full 27-day duration, but I was limited by computing resources, right? Because it's a lot. So the first thing we have to do is decide which orbits we actually need to stack at to begin with. So I was interested in just Neptune Trojans, so A in this range, E in this range, psi to give inclinations between about 45 degrees and 0, and true anomalies wherever. So I'm working with a grad student on this, and we're using an adaptive mesh refinement technique. So basically, you start with a hypercube where all the corners are at the very boundaries of these parameters that you want to search. And then you take two corners that they define 2 different orbits, and you ask what is the maximum deviation that those 2 orbits would ever have during the time baseline of your images. If it is more than epsilon, which here epsilon is about 1 PSF width, I use an arc second, then you make a subdivision, and then you keep going. And then once you're done subdividing, you have your set of orbits. We end up with about 122,000 orbits that we need to check over 1 week. You multiply that by the number of pixels that we're stacking. And yeah, so this is what it ends up looking like. Pretty cool. And then the next thing to do is to identify all image sets that we need to read into memory, because it's kind of a slippery problem. Which images actually correspond to the same KBO. So the way that I did that was I set up this grid of breadpoints to be dense enough such that I don't lose it. In a typical case, I don't lose any image overlaps that are larger than some amount. I think it was like 1 million pixels, okay? And then I take the corners of each image, apply the heliostack transformation that I just talked about, and synchronize them back to my epoch at which I'm stacking. And then for each of the red points inside of polygons, I do point and polygon tests and record which images, like which sets of images had more than, say, 10 images or something. And I repeat that for every single orbit that I want to check. So we end up with something like this. An image is 0, 3, 7, and 8, or whatever, and orbits 0 through 100,000, basically. So we end up with a lot. Yeah, so from these 42 images that I'm considering, 2,500 CCD images, they span 7 days, and they're in GRI and Z bands to make things more complicated. There are 312 unique image sets, and more than 20 million stacks to execute for an exhaustive search at 1 second maximum, 1 arc second maximum trailing. And it only took a few hundred lines of Python and Rust to get this done, which is pretty cool. So I did the full stack on 36 A100s in about 1 day, and it cost $50 on our cluster at school. Extending to 27 days would have been a factor of 64 more expensive, and I don't have that right now, because I'm a postdoc. So the basic procedure for each image set is that you read the image set into memory, pick an orbit, synchronize the corners of each image onto a canvas for the orbit, interpolate your image onto the canvas, accumulate signal, find the peaks that are above the threshold, run fast source rejection routines. I use dbScan and a convolutional neural network just to quickly eliminate junk. Write the sources to a catalog and then repeat step 2 until you're done checking orbits. So this is a typical signal to noise image. dbScan gets rid of the star stuff. Here's a real object that's stacking up. Here's another one. Here's another one. And I also keep track of the count image and the duration image. The counts tells me how many images actually correspond or contributed to the pixel, and the duration tells me the time between the first and last image. So the preliminary results, these rolled off the press about 5 hours before I could get on the plane to come here. But this is a super bright KBO that was found in a blind stack of 7 days. You can see here that there's different exposure times and colors and everything, so it's really complicated. But the mean and median stacks and even the individual frames are pretty easy to get here. But we also get stuff like this, where you cannot see it in any individual frame because it is fainter than, say, 2 sigma in every single frame. And I've stacked these up in 42 images, and I get signal to noise of 10 or 12. So this is the plant to fake with R mag of 25. And where previously my limiting magnitude was closer to 24. So in the stack of 1 week of data, I'm finding this stuff. So yeah, so it works. So the summary, linking is easier when you use an orbital invariance frame of mind to do it, right? Math is just easier that way. Linking the individual detections is mathematically identical to stacking. Long baseline stacking is very computationally intensive, even though it's possible. And HelioStack works, both for stacking and for linking catalogs. And we can link mixed catalogs where we have individual detections of the streets because you just assert a proper set of orbital invariants. So, yeah, that's it. And I'll take questions.
Thank you for the talk. It was super cool. I think you said that there was a one-to-one correspondence between a choice of R dot, R double dot, and
No.
A, E, F? No.
No, it's F. F is true anomaly. So RVR V omega corresponds to AEF. Where is it? Yeah.
Okay. Does that mean that linking in the first coordinate space is equivalent to linking in the second coordinate space with just a transform?
Yeah, this is a way to make the math convenient, right? So I just introduced this orbital basis because you can eventually get here. I don't know how else you would figure out how to get theta phi AEI and F, right? Yeah.
Thank you.
Great talk. So if you're trying to use the 4-parameter model, say you have x, y, v, x, v, y, and let's take LSST, say you have 2 observations one day, then another 2, and another 2. How sensitive are you to the astrometric error on that same day and getting that velocity there? So if you have error on that velocity, how good is the fit?
Wow. That's a very detailed question for a very eager talk. Yeah, so I don't know. I assume that it would work, but if your uncertainties are too large, you can't link stuff anyway, right? So it doesn't really matter. So I think this does as well as you can possibly do.
We have time for one more question.
So just going to the sort of the final result there of the stacking, you're, so you said, okay, so you're getting to 20th magnitude. And I'm just wondering, so how close to kind of like the theoretical limit of stacking you get when you do this?
Yeah, this is pretty close to the theoretical limit, I think, based on like a rough signal to noise calculation. Because say that I don't know what signal to noise this is because I was on the airplane while I was looking at it.
Okay.
But say it's 10, it's like a full magnitude fainter than before, so divide by 6. So 10 over 6 is like 1.3. So it would be 1.3 in individual images, which we were unable to.
Yeah.
Yeah.
Okay. I can see it in the 19th of November.
Yeah, that's a 300 second long R-band exposure. The other ones are hopeless.
Thank you so much for that.